All right, this is Mr. McMurray. We're done with chemistry for a while. We're going to start talking about, come down to earth, if you will, and talk about some geology, rocks and minerals in particular. Just like we talked about the atmosphere, we talked about, and we said about 75% of it, give or take a little bit, is nitrogen, and 18% or so is oxygen, which means way over 95% of it is just nitrogen and oxygen. You see kind of the same pattern in the Earth's structure. It's mostly just a couple of elements, all right, and not necessarily the ones we tend to think of most commonly come to mind. So first of all, there's iron. That's probably not too surprising. Iron is basically 1/3 of the entire Earth, including the crust, including the inside layers, and so forth. Oxygen, which we think of as a gas, which it is, but it's also combined with lots of things. Remember we did that in chemistry. We talked about sulfates and carbonates and all the different eights that have oxygen stuck onto it. So oxygen is very common. And silicon. Silicon we think of until silicon chips came along. And silicon was a very important ingredient in that, and then making transistors and all the chips and computer chips and so forth. It would probably be kind of ignored, but silicon is very important. Silicon and oxygen are very common ingredients in sand. Most common sand is quartz sand, and most common rock and mineral probably on Earth is quartz, or at least on the Earth's crust. And so that accounts for why silicon and oxygen are so common. Magnesium is also fairly important. Okay, it's 13.9%. Then it drops. Nickel's only 2%, calcium 1.8, aluminum 1.5, sodium 0.2. All the others combined are 1.9%, just barely 2%, all the other different ones. So even though we have 90 different ingredients, metals and nonmetals, to make things out of on Earth, by and large, and by a far margin, only a few of them make up the bulk of the Earth. All right. Now, it looks a little different if we break it down into the crust of the Earth and the inside core. In the inside the core, we have mostly two elements. We have iron and nickel. Okay, and so the inside of the core is very dense, very heavy, and we'll talk more about this later, but iron, as it turns inside there, it creates an electric field. An electric field, we know, creates a magnetic field. And so the Earth's magnetic field, we think, is caused by the center part of the Earth that's liquid and revolving around inside there, is what causes that core. Now, the crust, which is what we live on, just this little peel on the outside of the apple, if you will, this little layer here, very small part compared to the magnitude of the inside. Crust is a little different. It's mostly, almost, we would say entirely, if we had two elements, we would have to say silicon and oxygen. If you add those two together, you get about 74, about 3/4 of the Earth's surface crust is made of silicon and oxygen. Once again, we're talking about quartz here, and some of the very common minerals and rocks that contain silicon and oxygen. Then aluminum, iron, there's still some, although it's not nearly as common as inside the Earth. Calcium, sodium, potassium, magnesium, and then others make 1.4. Notice that some of the important ones, we'd say, copper, zinc, ones we've heard of and are used for things a lot, don't even make the list. They're very small percentages. But that's why when we mine these things, we have to find them where they're concentrated in certain areas, and even then we have to take a lot of rock and concentrate it to get those things. So of the 90 elements everything's made of, the Earth's crust is primarily iron, nickel, oxygen, and silicon would be the top ones, and thorium, magnesium make the top 5, but that's about it. Of all these different elements that make up the Earth's crust and its core, most of these are what we call minerals. Okay, by mineral, we can mean various things. For example, when people talk about vitamins and minerals, you eat all the vitamins and minerals you need, or you take a tablet or a pill that gives you vitamins and minerals. Basically, these are man-made nutrients, and they're usually in a form that's easily absorbed by our body, and so they're not what we call geological minerals. Okay, geological minerals, to be considered in geology, it has to be, first of all, it has to be a naturally formed material. Okay, naturally formed. It has to be crystalline. Remember we talked about ionic compounds that make crystal structures like salt makes a cube. Okay, they have to be crystalline, which just means made of crystals. All right, solid. Okay, they tend to be solids. Okay, and they have to have with a specific or definite composition. In other words, they're made out of a combination of a particular combination of elements. Okay, so for example, we said man-made minerals would not, for like a vitamin tablet, most of those are synthetic, so that wouldn't be concluded. A zirconium, cubic zirconium, which is made in a lab, okay, would not be considered a mineral. Why? Because it's man-made. Okay, so you see various jewels that are created in labs. Those are not considered mineral because they're not naturally occurring. They have to be atoms who are arranged in an orderly geometric pattern. Now, sometimes you see like the geode here, obviously it has some definite crystal patterns, and you can see that. And many minerals come in very pretty different shapes based on the crystal form. But some of them, the crystals are so tiny, they're microscopic, so you can't always see it with the naked eye. But they do have to have some kind of crystal shape, and they always have the same basic chemical composition. We can give a formula for their thing. For example, quartz is SiO3, which means it's made out of 1 atom of silicon for every 3 atoms of oxygen. Now, there can be impurities in it that give it colors. All right, and this is why you have gemstones that sometimes are in different colors. But basically, silicon, oxygen, is quartz. It's always going to have the same basic formula. Okay, so that's the specific combination or composition that we're talking about here. All right. All right. Now, going back to properties of minerals. What are some things that make minerals mineral? We've kind of talked about some of this. First of all, and how do you identify one mineral or from one rock? How can you tell the difference? Okay, so the first thing is the crystal form. Okay, what crystal form does it take? We already noticed that, for example, salt has nice cubes. Okay, it makes very nice cubes. But crystals, first of all, are caused by the orderly arrangement of the atoms on the atomic level. Okay, just like with sodium and chlorine, you have sodium with a positive charge, chlorine with a negative. You're going to have sodium attracted to that one, chlorine, and you could do that in 3 dimensions. You have a sodium plus the chlorine, and they would go in 3 dimensions, both out from the board and whatever, and so they're going to make a certain shape, and depending on how they're arranged, in this case it becomes a cube. Okay, but because of that, you're going to have it. Now, how pretty the minerals are, geodes are usually pretty nice because they have a lot of empty space. There's empty space in the rock, and as minerals leak in and the water evaporates, it leaves the crystals behind. A lot of the time you don't have that nice pretty well-shaped minerals because there's space constraints. Okay, they get crammed into another rock, and so when you look at a mineral, you may not see all these pretty shapes because they didn't have room to grow and make this pretty shape. Geodes, caves, like in the walls and floors of caves, are kind of the exception to the rule because there they have room to grow, and they also have time to grow, and they grow slowly over time, and so you get those real pretty crystal shapes. Now, the size of the crystals also depends on things. We evaporate the salt water very quickly, and so the crystals were very small. Okay, if the speed of cooling, okay, if things cool down very fast, say you have molten rock like lava or magma, and if it cools down quickly, okay, if it's very fast, you get very small crystals. very small crystals. Okay, so for example, when a volcano blows up and throws lava in the air, it cools down very quickly as it's going through the air, and so you get very small, microscopic sized crystals. On the other hand, if it cools down slowly inside the Earth, for example, a lot of magma just comes up closer to the surface but never gets up in the air. It stays in the Earth where it's still fairly warm, so it cools down slowly, and slow will get you very large and very pretty crystals. Okay. Now, as well as the speed of heating up or cooling, if it actually melts, many others just dissolve in water, and depending on the speed of how quickly it's dissolved, okay, of evaporating, how fast it evaporates. Okay, when we heated the water and evaporated off the water and left salt crystals behind, we had very small crystals. In fact, with the naked eye, you really didn't see big square crystals. If we could let the salt water sit for days and just gradually evaporate off the top, it would grow more orderly, big crystals that would be more impressive. The next property of minerals we want to talk about is hardness. Okay, hardness does not necessarily equal to strength. All right. Many crystals could be stomping under your foot, it would crush. Okay, that's not what we're talking about. Not how strong it is, but hardness is how resistant is it to scratching. Okay, is it easy to scratch if you're trying to scratch it, say with your fingernail? All right. And that is not the same thing as if you were to crush it. That's a whole different kind of thing. But hardness represents something that is very hard in resistance. The highest, we have a scale called Mohs hardness scale. Okay. Hardness scale. And on that scale, a diamond would be 10, and that would be the hardest, and talc, which is what we grind up to make talcum powder, so it's very soft, would be a 1. Okay, and that hardness gives you a scale of something to judge how strong it is in between. We use different things like a steel nail or a piece of glass or different things to scratch it and estimate where it would fit on that scale. Now, once again, it depends on the attraction. The stronger those chemicals are stuck to each other, then the harder that thing is going to be. If you have ions, which most crystals are, a lot of crystals are, okay, then it's going to have a very strong attraction, and they tend to be very hard. All right. On the other hand, if they don't have as great a charge between them, then they don't have as much of an attraction, therefore they're not going to do it. Basically, the size of the atoms has to do with it. The smaller atoms, or ions, they can pack tighter. All right, they can be more closely packed together in there, and because of that, they will attract each other more strongly, and they will also be tested out as being very hard. All right. And the last thing is, even if they're the same type, the closer together they're packed, then they are going to be harder. For example, graphite, which is a very soft mineral, is made out of carbon atoms, but the way they're arranged, they're not packed closely, tightly together, so it's very soft. You could write with it, you can scrape on it with your finger, whatever. Whereas a diamond is the same carbon atoms, but they've been arranged in such a way they're tightly packed together under pressure and heat, and they are very, very hard, and therefore one of the hardest things that we can come up with. The next characteristic we want to consider is, does a mineral have cleavage or does it have fracture? All right, cleavage is not the same thing as cleavage with people. All right, instead, in this case, cleavage means that minerals break smoothly along planes of weakness. All right, so break smoothly along planes of weakness. All right. Now, and it has to do with where you break. It's not the same as crystals, although sometimes they may be the same shape. Okay. Some minerals, for example, when they break, will always break instead of a cube, they're kind of slanted over like this, and that's the way they want to break. Okay, they may not grow that crystal shape, but anytime you break it, the pieces will break into that shape. Okay, so cleavage has to do with what shape do they break into when you break them. And generally, what that means is in these other directions, the bonds are very strong, but for some reason, the bonds that hold along this direction are weaker, and therefore they let go, and so they always